Hello, guys. Welcome back to African Motives, still on industrial electronics. And for that is working, this is actually DC theory because we've got a combination of the use of the Kirchhoff's law and also the application of the Thevenin's theorem. It was actually a combination of two on question number one. That is what we had, guys. Okay, so this 2022 question paper. So the first part, we are just given a circuit diagram. Then from that circuit diagram, we are given on 1.1, use the Kirchhoff's laws to calculate the current flowing across the 7-ohm resistor. In this case, we are working with the 7-ohm resistor, 8 marks for that. Okay, so let us check what we have, where we have got our 7-ohm resistor, analyze our diagram and see what is actually happening in this case. All right, so this is where we've got our 7-ohm resistor, but according to the currents, because here we've got V1, our positive is this side, negative, but on V2, this is where we've got our negative, our positive, which means the current is going to flow in this direction, all right? So from the positive side going this way, and here we are going to have it from the positive side going this way. So if you have to take note, let's say this is our current one, and this is our current two. As we said, it is going to flow out this way from the positive. So that's our direction of current. So B, from B to E, it is going to be current one minus current two, since these are opposing. So I want you to consider the question that we had. I actually had a question that was, I think, November 2016, similar to this one. So that's why I'm having this, so that you check properly. This is not going to be I1 plus I2, like what we had in the previous part that we talked about. So this will be I1 minus I2 like this. We are saying I1 is going this way, I2 is going this way. So I3 is going. So these two, if we are to add I3 and I2, these two, we must get I1. So it means to obtain this current, we are going to simply subtract, like what I'm saying, I1 is equal to I3 plus I2. So we are going to make I3 the subject. So transpose this to the other side, we are going to have I1 minus I2, which is equal to I3. So this is the one that you are given exactly, which is fine. So this time, we are saying we do not have a problem. The way our currents they are given on the diagram is fine. And if you have to take note, to find this, we need to calculate I1 and I2. So also the branches we are already given here. So I'm just going to take A, B, E, F up to A. So this one, guys, we talked about this. If you consider, so I'm not going to have much explanation here. So it's going to be A, B, E, F back to A. All right. So this is our positive side, as we can see, and the direction of current is fine. So the first branch, we've got 4 ohms and current 1. So we're going to combine these two, remembering that the voltage, the supply that you're going to have, which is V1, is equal to the sum of the voltage drops that you're going to have across that branch, across that loop, which is 18 volts is equal to 4 ohms times I1. So that is going to be 4 times current 1. We move on the branch from B to E, where we've got I1 minus I2 versus the 7 ohms. So it's going to be plus because we are maintaining the direction of the current. So that's a plus. So you're going to have plus 7 into current 1 minus current 2. All right, so combine everything, guys. Here we are going to have for current 1, 7 times I1. That is going to be 7I1, 7 times minus current 2, that's 7I2. So we can collect the like terms. In this case, we've got I1 and I1 in this case. So 4 plus 7, which is going to give us 11 in this case. 4 plus 7, that's 11. I1 minus 7I2. All right. So this is our first equation, which we can just rewrite. Maybe 11I1 minus 7I2 is equal to 18, but this part does not even affect our calculations actually. All right, so this is going to be our equation 1. The same thing from the other loop. If you consider B, C like this with the flow of current that you're given, so that it's going to be easier for us. I'm going to take this loop here. All right, so we are going to consider the loop B to C to D, E back to that point. So that's B, C, D, E back to the point B. All right. So in this loop, this is the direction that you're going to have. The direction of current is going to be this way. We are supposed to have it this way. All right. So still the same way, this time we're going to consider V2, not V1. We're considering V2. So our V2 is 12. That is 15, sorry. So 15 is equal to the voltage drops. So let's consider current 2 in this branch from B to C to D to E. That is current 2 flowing throughout this branch, and it's maintaining the direction of current. So that is going to be 12 times I2. So that's 12 times current I2. But if we consider from E back to B, we are going this way, but the arrow is opposing. The arrow that is we are given here, it's opposing, is going down. So we are going to subtract since we are opposing the direction of flow of current. So that is going to be a negative. So that's 7 ohms times the current, which is current 1, minus current 2. So this time, this is going to be a negative. So take note about this. All right. So anyways, let us combine and see what you're going to have. So because we've got our equations here. So 15 is going to be equal to 12 I2. Negative 7 times I1, that's negative 7 I1. Negative and negative here, that will be a positive 7 I2. Collect like terms. So I1 does not have any part, this part of negative 7 I1. So you're going to collect terms. I2 and I2 combined together, that's 12 plus 7. So 12 plus 7 is going to give us a 19. So that is going to be 19 I2 like this. All right. So just like the previous part, we can just rearrange starting with negative 7. So this is going to be negative 7 I1 plus 19 I2, which is equal to 15. So like I said, on how you are going to solve for I1 and I2, this is up to you. Your method, the method that you choose, because here these are simultaneous equations. So you use any method of your choice. But remembering that by finding I1 and I2, we are going to subtract them to find the current in the 7 ohm resistor as given from our diagram or from the understanding of the Kirchhoff's laws, that is the current law. All right. So in this case, in the last part, I used the substitution method. So this time I'm going to choose another method, elimination method. This time, okay, I'm going to take the first equation. This is 11. So I'm going to take this as 11 I1 minus 7 I2 so that you just learn different methods. All right. So here I'm going to use another method this time. All right. Plus 19 I2, which is equal to 15. So like I said, I'm going to use elimination method. All right. So these are the two equations that we had before. So from these two equations, like I said, I'm going to use elimination method by elimination method. All right. So there's so many methods, guys. Make sure that you watch the videos on how you work these ones. Okay. So it depends with what you want to eliminate. Do you want to eliminate I1 or I2? Depends. So in this case, I'm going to eliminate I2. All right. Let's say I want to eliminate I2. That means I'm going to find I1. If I eliminate I2, I'm finding I1. So to eliminate I2, just here there's 7. Here there's 19. So you're going to just interchange these numbers, 7 and 19. So on top, you multiply by 19. Below, you multiply by 7. So if you can reduce these, yes, you can reduce them. But in this case, we can't reduce 19 and 7. So 19 multiplies everything on top. 19 multiplies everything on top. So it's 19 times 11, which is 209 I1. 19 times negative 7, which is negative 133 I2. 19 times 18, which is going to be 342. 7 times negative 7, that's negative 49. I1, 7 and 19. This is going to be a positive 133 I2. Then 7 times 15, which is going to be 105. So 7 is multiplying everything. So these are the two equations. As we can see on current I2, the one that we want to eliminate, we have got 133, negative 133, positive 133. So you just ask yourself, am I going to add these two so that I can eliminate I2, or am I going to subtract? So you can try, let's say negative 133 plus 133. Are we going to obtain a 0? That's a 0. If we subtract minus 133 minus 133, this cannot give us a 0. So in order for us to eliminate I2, we are going to add the two equations. So here we are going to add addition gives us a 0 here. So we're going to add. All right, so let's add 209 plus minus 49. We add 209 plus minus 49, which will be 160. So that will be positive 160. 209 minus 149 is going to be positive 160 I1. So like I said, if we add these two, we are simply eliminating to remove I2 actually, okay, to get rid of current 2. Okay, 342 plus 105, we are going to obtain 447. All right, then divide by 160, both sides divide by 160, we've got I1. So current 1 is going to give us, that will be 2,79375. So 375 is going to give us 4. So that will be 794. So it is going to be a 4 in this case in amps. That is to 3 decimal places. Okay, so it depends with the instruction that you're given. Is it to 3 decimal places or so forth? So after finding I1, we eliminated I2 to find I1. So to find I2, you can simply substitute now I1 in any of the given equations. This I1 that we got, you can substitute in any equation that you are given. So thus you choose any of your choice from this, any part that you're going to work with, okay? So in this case, I'm going to substitute into equation 1, all right? From my equation 1, did I even write these equations? All right, equation 1 is this one, 11 with the 11, this one on top. So I'm going to substitute on that one. So this is my equation 1. This is my equation 2. So you just substitute into any of these equations, all right? So if we substitute this I1 that we got here, which is we are going to have 11 I1. So this is supposed to be 11 I1, but I1 is now given as 2,794. All right. So we are going to multiply this minus 7 I2. So that's minus 7 I2 is equal to 18. So by this, we are left with only I2 in this case. So we are going to find I2. All right. So you can solve, or we can determine the value of I2 in this case, multiply or transpose everything. If you multiply the first part, you're going to obtain something like 30,734 minus 7I2, which is equal to 18. So minus 7I2 will be equal to 18. Then we can transpose this part here because we want to remain with I2 in this case. So if we transpose this, it will be a negative on the other side if it was a positive. So this is going to be negative 30,734, which you are just doing on your calculator. These other steps, there is no need for you to show them. Just use your calculator direct, all right? So 18 minus this 30,734 is going to give us negative 12,734. All right, so that's 734. So you can divide by negative 7 from our calculator. We are going to obtain the value of current 2, which is going to be 1,8194. So that will be 1914. So there's 14 there. So the 1 cannot change the 9. So it will remain like that. That is 1,819 amps. So this is our current 2 in this case. But remember, this is not the question. The question is to find the current that is across the 7 ohm resistor. All right, let's get back to our question here. The current across the 7 ohm resistor, this is the one that we need. And the current is referred to as I1 minus I2. So we are going to find I1 minus I2 in this case. All right, so the current, therefore, the current through, so you're going to have the current through the 7 ohm resistor. The current through the 7 ohm resistor is going to be given as I1 minus I2 as we are given on the diagram. So you're just going to subtract I1, which is 2,794, this current here, minus I2, which is 1,819. So this is going to give us I2, which is 0,975 amps. All right, so that is the current that is flowing through the 7 ohm resistor in this case. All right, so this is how we can apply or use the Kirchhoff's laws. So this one is just a basic understanding from our N3. So if you are to check here, guys, make sure of the information that you're given on the diagram. Yes, it's very, very important that you note how you're given your information, then work through that information that you have got. Okay, on the same time or on the same question that we are given here, we have got the application of or the use of the Thevenin's theorem in this case now. Consider the circuit in question 1.1 that we had. Use Thevenin's theorem now to calculate the current across the same resistor, which is the 7 ohm resistor. Assume that V1, this take note, assume V1 has an internal resistance of 1.5 ohms. So take note that V1 now has an internal resistance. All right, so this is what they mean on our V1 here. So you're just going to have R there. Remember, the internal resistance is given as R. So R, the small letter R, which is 1.5 ohms. So that is what we are given. All right. But the question is to calculate the current across the 7 ohm resistor. But this time we are applying or using the Thevenin's theorem. All right, so remember what we've got on our Thevenin's theorem. I explained these stages before, what you need to find or how do you gonna find it. Also, remember the first stage is to find the VThev, but this is considered by removing the load resistor. So we're going to remove the load resistor, which is the 7 ohm. So we remove the 7 ohm resistor. By removing the 7 ohm resistor, we are going to represent it across AB, but this we are going to calculate VThev. All right, so if we remove this 7 ohm resistor, we're going to remain something like this. We are going to have here, take note of your voltages, the way they are given, positive, negative. So if we combine now, remember we have got the internal resistance, and also there is a 4 ohm resistor. So these are in series. So we're going to add them. 1.5 plus 4 ohm, which is going to be 5.5. So this one, it is going to be represented now as a single resistor. All right, but remember we said we want to remove our load resistor, which is, and we replace this with AB. All right, so that's our AB. The other part is going to remain as it is from this side. We are going to remain. Also take note, this is a negative and a positive like this. All right. Then we've got our resistor like this. All right. This is just a sketch, guys. All right. Do not panic. All right. So the voltage here is 18. So we've got our 18 volts, and we combined these two to make up 5. That is 1.5 plus 4 to make up 5.5 ohms. So this will make up 5.5 ohms. And here we've got 12 ohms with its voltage source of 15 volts, which is our V2. So this is our V2, our V1. So take note, we are supposed to find VThev in this case. We are supposed to calculate VThev, which is the voltage that we are going to look it across here. That's our VThev. How is this possible? How is that possible? Okay, what you're going to do in this case, you're going to use the voltage divider rule, which is that you're going to find the voltage across, you assume as AB and BA, all right? We're using our voltage divider rule. So here, okay, V1, okay, let's take note from our diagram. Okay, that is 18. Okay, here we've got 18 volts, all right? So we are going to consider first the 15 volts, which is our V2, considered at across the voltage, which is BA. All right, so, okay, let me explain it this way. We are going to consider V1 out. All right, so if we consider V1 out, we are saying V1 is not there. Like we just say this part is not there. We are going to calculate what we refer, okay, we are going to calculate the voltage across BA, B to A, all right? So that is going to be VBA. So this, we are considering like V1 is not there. This voltage one is not there, okay? We calculate VA, VBA, whereby we are simply using the voltage divider rule. Remember from our N3, the voltage divider rule, that is the voltage, the resistance across that part that we are calculating the voltage, all right, to the other resistor where we are given the voltage. Because if we consider V1 out, it means the V2 is there. Because V1 we are saying it's not there for now. So we are considering V2. So this is going to be 5.5 over the sum of these two resistors, 5.5 plus 18 times the 15 volts. So this is going to give us something like 4,714 volts. Okay, so this we just write as VBA. All right. We calculated this considering V1 as if it's not there. So we are going to have the same thing or same application to consider as if V2 is out now, is not there. But what are we going to do now? We are going to calculate the same concept, this time we are going to calculate VAB. All right, so we're just going to write this as VAB, which means V2, this part, we are not considering this. We are considering V1 this time because we are saying V2 is out. It's not there. So how are we going to find this? VAB, just like the previous part, this time, we are considering the resistor of 12 ohms. This 15 is not there. So it's like we are calculating voltage across here. So we are considering 12 ohms this time. All right. Meaning to say our V2, our V2 is not there. So we are going to calculate VAB. Our VAB from our voltage divider rule is going to be 12 this time on top. So that will be 12 over the sum of these two. So that will be 12 plus 5, that is 5,5 in this case. All right, 5,5. 5,5. Sorry, guys. On my preparation, I did this properly. Now, this, I don't know how did I write 18 instead of 12. Here, this is 12, guys. Okay. Here, this is 12. The resistance is 12. Okay. So just take note here on that part. This is 12. Can we correct this part? All right. This was 12, 5,5 plus 12. All right. I don't know how did I add that part. All right. Anyways, we are going to multiply to the voltage that we are considering now because we are saying V2 is out. So we are considering V1. Our V1 is 18 volts. So we are going to multiply by 18. That's, I think, how I wrote this part. You know, this is a resistance. All right. So this is going to give us VAB. All right. So our VAB in this case is going to be VAB. That's 12 over these times are 18. Which is going to be something like 12,343 volts. All right. So this is what we got here, guys. I think our voltages are now fine. So in order for you to have VTEV, guys, this whether you know the formula or not, just consider to say which one is the biggest between these two. But the actual formula that we are supposed to have for VTEV was supposed to be equal to VAB minus VBA. But in this case, consider the bigger voltage minus the smaller voltage. Our bigger voltage is VAB. So that is what you're going to do. You're going to subtract the smaller voltage from the bigger voltage. So that's 12,343 minus 4,714 volts. All right. So if we do this, we are going to have our VTEV. All right. So our VTEV in this case is going to be something like 7,629 volts. All right, so just consider also rechecking our calculations to see if we are also in the same page or on the same page in this case. All right, so we calculated the VTEV after removing the load resistor, the one that we are supposed to calculate the current across. So using the same concept, remember from our Thevenin's equivalent circuit diagram, we also need RThev there. So how do you find RThev? Remember to find RThev, you remove the voltage sources now. So now we are talking about the voltage sources. But wherever there is a resistor, you're going to replace with a resistor that is there. So here, we are going to consider removing the voltage sources. Let me just write here and see if we are going to win. Let's just hope we are going to win this time. All right, so let's put it this way. So this time we are going to remove the voltage sources. All right, so these are voltage sources. So where there's a resistor, you just have that short circuit there, replace with the resistor that is there. So you just maintain with the resistor. So by removing these voltage, what are we going to do? We are going to calculate RThev. Calculate RThev, the Thevenin's resistance there. So let's consider the first branch, V1. If we remove V1, we just remain with the 5, remember the 5,5 was a combination of that internal resistance that we added. We said there was an internal resistance and we added 4 that gave us 5,5. So as we are focusing on this diagram here, so if we remove 18, we remain with 5,5. So here we are going to remain with a resistance of 5,5 like this. All right, we move on A and B as they are. So A and B, they're just going to remain as they are, A and B open. So this is what we're gonna have. And we move on, we remove the 15 volts. That means we remain with a 12 ohm resistor. So we are going to remain with a 12 ohm resistor in this case. All right, so this is what we are going to have. We remain on this part with the 12 ohm resistor. So this will be our circuit diagram. We've got the 12 ohm resistor here. We have got the 5,5 ohm resistor, that combination of the 4 ohm resistor and its internal resistance. So this is what we have. So the question is, what is going to be the resistance in this case? Remember here, there was actually like a resistance. So these two are considered in parallel. So meaning to say our RTF is the R parallel of the circuit, whereby we know that R parallel is simply the product over the sum of the resistors. All right, so that is how we are going to calculate RTF. In this case, we are going to use the product of the two resistors over the sum of the two resistors. So that is RTF. We multiply 5,5 times the 12 ohm resistor over 5,5 plus the 12 ohm resistor. So this is going to give us RTF in this case, which is, if we reduce this properly, our RTF is going to be 3,771 to 3 decimal places, which is ohms. All right. So with this information that we have here, guys, with this information that we have, this is enough. We have got our VTEF, we have got our RTF in this case. With this, we can now represent on our equivalent. We are supposed to know this equivalent circuit diagram by heart. All right. So our equivalent circuit diagram, remember, it consists of the VTEF. All right. The VTEF and RTEF like this. So this is what you're going to have. And that part that we removed, the part that we removed, I'm going to show you later on. So this is our RTF, which is this one, that is 3,771 ohms, and our VTEF, which is 7,629 volts. But remember, we had that AB open that we removed. Now we are going to replace it, which is the 7 ohm resistor. If we take from our diagram here, we are talking about the current that was across the 7 ohm resistor, and it was just only the 7 ohm. We are not having any other resistor, so we are going to replace back our 7 ohm resistor. On the equivalent circuit diagram, you replace back the original circuit that we had, I mean the resistor that we had. So this I'm just going to show you as this so that you do not confused. So this, you're going to replace it back on your point. This is our 7 ohm resistor, the one that we need. So the question is to calculate the current flowing through the 7 ohm resistor. But as you can see, the current flowing through the 7 ohm resistor is the same as the current flowing from this point, which is the supply current, because this is a series circuit. The current here is the same. So meaning to say the current through the 7 ohm resistor is equal to the total current in this case. So meaning to say we can calculate the total current from the voltage. We have got a VTEF over the total resistance. Our resistance, we've got RTEF plus the load resistor, that one that we removed, which is RL. So this will be our formula to calculate that current. So you add all the resistors together. So meaning to say our current is going to be VTEF, which is 7,629 over the total resistance, which is RTEF. Our RTEF is 3,771 plus RL, which is the total resistance of 7. So in this case, if you combine everything together, that will give us the total current through the circuit. All right, so that is going to be something like 0,708 amps to 3 decimal places. So therefore, we have calculated the current in the 7 ohm resistor, because we are saying the current in the 7 ohm resistor is the same as the total current. So therefore, the current in the 7 ohm resistor is going to be 0,708 amps. That is what we had in this case. Okay, so these are typical questions that we have. So as you can see, this is Feb 2022, meaning to say now you must expect questions which combine the same plot, maybe Kirchhoff's superposition, Kirchhoff's Thevenin, just as long as it's part of the DC theory, just expect a combination of the two, all right? So it can be any part or any theorem that you have or any law from our Kirchhoff's laws and all those other theorems that you're going to have. But this is what we had, guys. Also take note of your questions, how you are given. This time we are given a certain additional part which was important, that the assume that V1 is an internal resistance, which means at V1 here we are having 1,5, but already across this branch there was a 4 ohm resistor. So do not neglect that part. We are supposed to add it into consideration. Okay, anyways, guys, that's what we had from Mason African Motives. Till we meet again.